Hello, my name is Carlos, and I am the leader of the Embedded Systems team in charge of implementing the microcontroller units.
Hello, my name is Saul, and I work on the development of the YOLO architecture, and I'm the leader of the Total Bolts team.
My name is Yurisa, and I work in the localization system for the underwater vehicle.
Hi, my name is Andres. I am the current captain of the RoboSub team, and I work on the control system and the detection of the path mark.
Hi, my name is Sebastian, and I work on the development of the gazebo simulation environment and in the mission algorithms.
Hi, my name is Edison. I worked in the missions algorithms inside the gazebo simulated environment.
Hello, my name is Francisco, and I'm currently working as a software developer on the perception of the underwater vehicle.
Hi, my name is Ivan Diaz, and I work on the development of the YOLO architecture.
Bantech began participating in RoboSub competition in 2020. Last year efforts rendered solutions to the gate, voice, and torpedo tasks, with limited validation due to the sudden appearance of the pandemic. The previously proposed guidance and control system proved enough to complete the state task in simulations, but did not consider inputs from the perception nor state estimation systems, as they were not developed yet.
The speed and position PID controllers remain in charge of the vehicle's motion control. This system will rely on an IMU VN200 and a bar theory pressure sensor for position and velocity feedback.
The perception system is achieved using two main sensors, the CED mini stereo camera and a Raspberry camera module V2, being positioned at the front and at the bottom of the UUV, respectively.
The perception system has two functional object detection methods which can be used at the same time according to the task. The first one is YOLO, a convolutional neural network trained to detect competition props using the input image of this front stereo camera. And the second one relies on the set mini 3D point clouds to identify props depending on its shape.
To accomplish the handling of peripherals such as the hydrophones, the leak sensor, and the depth sensor, a STM32 unit was acquired. The STM32 microcontroller was chosen for its computer power, sampling precision, and large number of programmable pins.
The embedded system achieves a multi-threading environment in a one single processing core by using a FreeRTOS environment. The tasks are done by one or multiple threads, and the system scheduler manages them for a correct operation. Each sensor has its own task where the received data is interpreted and, if needed, a response is given.
As health restrictions were still present at the beginning of the year, physical development was considered, but did not take a major role in the planning of the project. Approaches validated through simulations and theoretical design were the go-to solutions for most systems for this competition.
Work made for the previous competition rendered solutions for the gate, buoys, and torpedoes challenges. These solutions validated the general algorithms for each challenge, but did not consider inputs from a perception system. Also, a state estimation system was not developed at the time either, because the simulated UUV model could provide the required data.
Given the background of the project, it was deemed necessary to give focus to the development of a perception system, capable of identifying the different props presented in the competition, and a state estimation system to obtain data such as position, orientation, and velocity of the vehicle. Though the last one would only be necessary in the case of a physical event.
Also, due to limitation caused by health concerns, a simulated environment was developed for testing, on which we will further talk upon in the next developing and testing segment.
Efforts were made to develop the state estimation system for the vehicle with said simulation environment, but for a number of reasons, the project was not completed, although it does not present a big concern for this competition.
To increase precision of the detection of game elements such as the buoys and the gate, we implemented a Euclidean clustering algorithm configured specifically for our needs, as well as some subroutines to discern which object is which. The resulting routine is a fast, low-cost approach to detect three-dimensional objects. As for the projectile targets, we used a fast color thresholding method to acquire objectives swiftly. We leveraged the difference in relative position of each target to identify them, since the circular hole is always on top of the polygonal one.
Last year's approach for the YOLO neural network relied on training based on a synthetic dataset. But when we tried to test that network on the simulation environment, we realized that it yielded poor performance.
For the previous reason, a new dataset was created based on the simulation environment. That approach was chosen first, as access to a pool was not possible for a real dataset. Second, there was no reason to develop a synthetic dataset with last year's approach, as no physical competition will take place, and third, it was easier for the new members to learn the appropriate process for the next competition.
The final objective for this competition is to further validate the gate and buoys challenges, as well as the path marker guidance, mainly with a new perception system in the simulation. Solutions for beam and torpedo challenges are also proposed, but further validation with the perception system is required.
The developed perception system proved enough to complete the gate and buoys challenge. The system is capable of detecting the gate and buoys through the processing of the stereo camera point clouds, yielding waypoints for both sides of the gate, as well as waypoints for each buoy. Afterwards, the YOLO network provides the chosen waypoint to the guidance system, depending on the function of the UUV.
Also, a detection method was developed for the path marker follower, where the algorithm looks for the characteristic edges of the markers with the bottom camera image. Once the marker is identified, its rotation angle is calculated and used to create a waypoint in the same direction. This method does not require YOLO neural net, saving processing resources.
For the beams challenge, the robot navigates through the simulated environment until it finds a shape similar to the beams. Once the beams are detected, the submarine will position itself between them. Later, the submarine proceeds to search the required image with the pre-trained neural network. A solution for the mission is proposed, but further development with the 3D perception system is required.
In the torpedo challenge, the stereo camera point clouds are used to detect the rectangle shape of the shooting board. Afterwards, the robot orbits around the board until the neural network identifies the image. Then it remains at that position and shoots the torpedo. The perception system is currently able to identify the shape, the image of the board, and the openings, but further work is required to unify the solution with the perception system.
For embedded systems, the objective was to improve the design from the previous year. Because of health restrictions, the objective was limited to just implement the fundamental sensors and actuators, such as the depth sensor and the motors.
In order to leave a window for further testing and optimization, a real-time operating system was implemented on the microcontroller. With RoboSub, we can handle the required component while managing hard time constraint and component priority.
With the current pandemic, physical development was not possible due to health regulations established by the state government. In the end, this lowered the worry of developing a complete physical system, so the focus shifted to development in a simulation environment.
The development of both the FreeRTOS environment and the task was done in the STM32Cube IDE. The approach taken was to develop a task for each sensor while bearing in mind that change and optimization will be needed. The same could be said about the CAN communication protocol we developed this year.
The simulation approach was similar to last year's, and RBIS was used as the visualization tool for some mission algorithms in early stages. To develop the perception system, the use of Gazebo was required, as it allows to simulate vision-based sensors such as the SET mini camera. Animu was not required to be simulated, as its data could be obtained by using the mathematical model of the UUV.
It is in Gazebo where we were able to measure the viability of our mission algorithms and system implementations, such as the new perception and guidance method.
Also, worlds in Gazebo were created where full models of the challenges and the UUV could be found to provide our developers an easier and faster way to test their implementations for the designated tasks.
The simulation results show the capabilities of the proposed task solutions for the gate and buoys challenges. Results show that approaches for the UUV systems work, but will still require physical testing to completely validate the proposed solutions.